I'm Hirokazu Shirado, Assistant Professor at Human-Computer Interaction Institute, Carnegie Mellon University. Today, I'm introducing the two studies from my work on this theme, social dynamics of human-AI hybrid. I'm obsessed with social networks and human collective action. Humans have evolved the ability to form complex networks of social connections. However, interconnected group of people face challenges in social coordination and cooperation. Individuals may see no optimal way to act when individuals and group benefit are not aligned. So my lab has exploring the potential of machine intelligence, specifically AI agent and assistant, to address the challenges of collective action among people. So my talk can contribute to this transboundary workshop and human augmentation research by introducing the social aspect of human-AI hybrid. We mainly use virtual lab experiment to approach this theme. We recruit participants online and let them play interaction games in groups, though where we sometimes add computation component, such as bot. Participants try to work together in the interaction game with real economic stakes, so real money. Within this basic setup, we examine how experimental treatment, including bot, change human decision-making and collective actions. Online settings allow us to examine such causal relationships through many repetitions under experimental control. These findings can supplement observational studies by giving clear causality in the complex social fabrics of human and machines.
So let me explain about that. So using this type of the online experiment settings, we've been studying hybrid social networks in which human and machine interact on the equal footprinting. With the development of machine intelligence, machine can now behave as actors, somewhat automatically and influence human decision-making. Also, importantly, human can also take machine as actors through interaction on social networks, such as bot on social media. So in this venue, I've studied various collective action challenges and specifically what behavior policy of artificial agent embedded in a network can change social dynamics among people. So as an example, let me introduce a top study on the list, which was published in Nature in 2017. It's a little bit old study, but later I'll also show some new study from this venue. So in this study, we explored a way to address the failure of social coordination by partial optimization. So narrowly focused workers might enhance labor to their own productivity, but this might actually decrease overall group performance. I came up with this research idea when I worked for Sony Corporation, and Sony's economies went down severely at the moment. At the moment, I didn't think that Sony's workers did not work properly in their division. They actually work harder, but still, Sony in large really bad. Why? This is partially because of this partial optimization program. More generally speaking, even if all individuals behave properly in local interaction, this may not result in the optimal outcome for the entire community. So that means, for example, with human augmentation, maybe each individual improve individual capability, but which does not result in the collective outcome on the entire population. I know it's a little bit surprising, but we often face this type of challenges in everyday life. So my research question is how specific individuals can facilitate collective action to solve this coordination problem. In practice, it's challenging and costly to observe an entire social system and to manipulate people with godlike power. So that means, for example, of course, we can change, for example, network structure in a specific way. Or we might change the payroll structure to give some incentive for cooperative workers. But it's really hard to do that in practice. How can we change our network structure? Do you like that? No. So my point is that how each individual like us can change the dynamics of collective action. It's really hard, But we have to do that because all our behavior and influence are embedded in social networks. You cannot decide on their own. So to understand the role of individuals, I use a bot in social networks experiment and made them interact with real human participants. This study was one of the initial trials addressing the social dynamics of human-AI hybrid. At this study's interaction system, I used a color coordination game. It's a very specific game to study social coordination. This game was inspired by the graph coloring problem in computer science. Did you know the graph coloring problem? Please raise your hand if you know that. Yes, this is NP-hard problem. That means that no efficient algorithm to exist to address graph coloring problem. Then one research group is that actually this is Michael Kahn's group is University of Penn, UPenn, develop the experiment paradigm based on the graph coloring problem to examine the social coordination. They simply said, hey, how human can good enough to address this graph coloring problem in distributed system. So let me explain about how the game looks like. Players are assigned in a node of a network, and in the game, each player select their node color from 3 options. In this case, is orange, green, and purple. The game's goal is for all players to select a different color from their local neighbors. Okay? So, for example, if all the players like this, if you can see each node, every node select a different color from their immediate local neighbors, right? For example, here, this player orange, they're all the neighbor green, purple, green, purple, green, purple. Okay. If every player, everyone can select a different color from their local neighbor like this, the game is finished. Then the problem is solved. But even at least one color conflict like this, the orange guy in the middle, the game is still going on, and everybody have to play this game to solve this color coordination problem. The point is that we researchers can evaluate the group level of social coordination by measuring the time it takes to finish the game. So here it measures the group level coordination, not the individual level. Okay? One note is that in my study, we created all the networks using the preferential attachment algorithm in the network science. Yeah, you don't necessarily to know about what the algorithm is, but point is that it allows us to create a different network topologies every time with the same number of the node and same number of the edges. Also, it mathematically guarantees all the networks have at least one solution for these current games with 3 colors. So that means that in our study, all the networks are solvable. Okay? All right. So let's see how participants solve during the game. There are 3 key points about the gameplay. This is the actual game view for the online participant in my experiment. First, player cannot see the global situation. You can, for example, here is this player can see their own color and also 4 local neighbors. Okay? But they know more than others outside of the color, outside of the 4 nodes. And also, player can choose their color anytime they want. Okay? Full autonomy. You can choose anytime you want. You can see like now this person choose a purple, but other people also chose the purple, so that means that person have local conflict. So yeah, this is a problem. Then you can see, second point is that you can see this counting timer, also plus the bonus, the actual money stuff. So that means the time this counting timer started from 5 minutes, then to going down. The bonus number is 2. Okay, so that means if the player solve this game, for example, now 3 minutes 46, the player can earn $2.26. But if this player cannot solve this game in 5 minutes, the bonus is 0. You cannot earn anything from that. So that means the player are economically incentivized to solve this game as quickly as possible. The third, player have to work together as a group to solve the game. If they cannot solve the game without even single conflict in the entire group, all the players don't get paid. So for example, even if, for example, this neighbor chooses orange, then in locally, all the color is solved, right? But probably you still get this message. Some players still have color conflict, the game is going down, and your bonus is going down. So that means that all the players have to work together to solve coordination problem with limited information, with incomplete information, because each player cannot see the entire network. Okay, let's see the gameplay of actual participants. There are 20 human subjects here in the network, and at the beginning of the game, the node color is randomly assigned for each subject. So there are a lot of color conflict. You can see that there are a lot of red edges, right? Because I randomly assigned to the color. Then again, as I mentioned before, when all conflicts, so that all red edges are gone, then the game is done. You're completed. Let's see how people react to this interaction system. This is real time. You can see that humans are good enough to try to remove their local conf very quickly, right? But sometimes they are stuck on that end. Then they try to the new color configuration. Then they are stuck again. Then you can see these players solve their local conflict for a long time, but because the other parts still have a conflict, their bonus is also going down. So probably these guys couldn't understand why the other player could not solve this so easy game, right? You just pick different color from their local neighbor, but see, this session still haven't solved over 4 minutes. Okay, so it can see the game is come on. So yes, but you can see that almost close to the allotted time, 5 minutes. Okay, so locally, you can see that so simple, so easy game. You just pick a different color from their local neighbors, but globally, sometimes it's really hard to address that. So let's see, here is a sample comment from actual human players after the game. So top 3 come from, you can imagine, like an unsolved game. So they cannot solve this game in 5 minutes. The last one is come from the solved game, okay? You can see very different tone from top 3 and yeah, you can see like a very emotional reaction to simple game. For example, first one says someone is a useless idiot and it's not me. But when we analyze this data and to find out, actually this guy is a bottleneck for solve the game, right? So that means this is a funny, but actually this represented actual coordination problem. So that means everyone, including a bottleneck useless idiot person, did not understand why this coordination is optimized. Okay? So the color coordination game emulated real circumstance of social coordination as objective behavior phenomena. So that means local in a suboptimal situation and as subjective psychological distress. So everyone could understand why this so easy coordination cannot be optimized. Okay, so as I mentioned before, using this color coordination game, we evaluated network intervention to improve group coordination using bot. So we put 3 bots in social network having 17 human players. So that simply say, I replace 3 human subjects with a bot. Then because of that, we're using a bot, we can control the bot behavior, so bot policy and the location of bot. How can we improve this coordination? How we can accelerate this coordination process by manipulating bot behavior? Okay, that's a breakdown, the research question. So probably you can imagine, oh, if I were researcher, what behavioral policy can be possible to accelerate the coordination problem? Okay. So to consider the bot parameter, we examine the social coordination process of only human networks, like you saw, like animation. Then we observe a lot of like a human-only sessions several times that we found that this issue is actually sub-optimization problem. For example, in this situation, all the players, including the central orange guy, selected their best color, which means at least conflict color with their neighbor. So if this either way, the orange guys change the color from green and purple, their local conflict increase, right? That's why they selected orange color. So that means all the players actually are rational. However, the game hasn't solved. But I told you, all the network of my study are solvable. All right? So that means that even all of you are rational and choose the best color in their local, sometimes you are stuck in the local end. So this difficulty can be seen as a challenge of global optimization. This is a simple illustration of solution space. It contains two locally optimal states separated by a bump. Point A is a local minimum, but point B is a better. So the system needs something to escape from point A to point B. Probably you heard this type of the lecture in your 101 courses before, because this is very simple issue, is a global optimization. According to prior theoretical work, noise can work in this situation. For example, in biological mutation, in biology, mutation, which is a kind of a genetic noise, has an essential role in evolution. In the field of computer science, probably many of you, randomness can facilitate information search. So sometimes you integrated some randomness component in your algorithm, right? Yes. And also noise can be seen as a heat that make particles move in physics. So our idea is to apply the functional role of noise to our social world. However, that sounds counterintuitive and even paradoxical. Some random behavior in individuals that are seemingly human errors actually improve our social coordination ability. So that tension between ego and group is indeed a collective action. So we tested the noise effect by manipulating a bot behavior. This is a control diagram of how bots play in the game. Probably many of you designed this control diagram in your study. I think this is the simplest one, the only two errors. So let's say, example, if 0% noise condition, that means that this p random is 0. So that means it's always to go this way. The bot always choose the best color in their local. So that means that the bot is most rational and the perfect bot for their local interaction. Then 10% and 30% condition with some random occasion. Bot just randomly pick one of three colors to choose that. Okay. Then at the time, they choose the best color with the same diagram. Yeah. Okay. Independent of the noise in the bot behavior, we also manipulate the location of these three bots in the network based on the number of neighbors. That is degree centrality in network science. A random center is having the most connection, and the periphery means having the fewest connection. So in sum, the treatment of both the three levels of behavioral noise, 0%, 10%, 30%, by three bot location is that random, center, and periphery. And sorry about that. Okay. And also we have a couple of control and supplemental experiments. Then in total, we conducted the experiment in 250 sessions with over 4,000 participants. So in other words, we created 250 small virtual society of over 4,000 real people. So this is the main result of the experiment. I know it's very complicated. So let me explain little by little. The lines are survival curves of the session at group level. The y-axis shows the survival proportion. That is percentage of the unsolved session within the game time indicated by the y-axis. So to explain what that means, let's see the detail of the light blue line. So light blue line is only human sessions. So that means unrelated to bot noise and bot location. And you can see all the light blue lines are identical. I just putting the light blue line, just comparison for all the cells. So let me take the central cells, light blue line. So when the game started, like here, all the game unsolved. That's why 100%. Then when the time goes by from 0 to 300 seconds, so that means 5 minutes, some sessions are solved during the game. So that's why this curve is a little bit go down. Then at the time of the limited time, 5 minutes, 10 of 30 sessions, that is 30% of sessions are still unsolved. So this here, right? So in turn, as for the survival curves, the steeper slope means the game is likely to solve quickly. That indicated higher level group coordination. So that if the slope is more steeper, so that means the game is more likely to solve with a shorter time. So that indicated a higher level of social coordination. Then let's see the dark blue line, which is a session of human and bot having indicated behavior noise and geodesic location. The p-value are given by the very simple log-rank test to compare the two survival distribution between light blue line and dark blue line. So as you can see, the session having bot with 10% noise and central locations were the most likely to be solved within the allotted time, allotted 5 minutes. The solution time reflected a significant improvement compared with a session without bot. So that means that with the 10% noisiness and central location, but actually significantly accelerate the coordination problem compared to the session of only humans. The result supports the hypothesis of positive impact of behavioral noise on human coordination, but only in the central location. Why? Of course, in the theory, I explained that. Why empirically do the bot with small noise at central location improve group coordination? Here, a hypothetical network for data visualization. As I told you, in the experiment, I created network different topology. But here, for the comparison, I show the same network across the 3 and located central for bot. But then the color is not their choosing of color. So the color indicated how deviant behavior they take compared to the only human session. So that means that if the node color is more red, that means that people choose more long color. Choose long color more frequently. Okay? The red blue color means that people choose long color less frequently compared to the session only humans. So that means that these color differences show the influence of both. Okay? If there is no influence, the color is white. Okay? Then with 0% noise bot, so that perfect bot here is that actually the bot also reduce the noise of human decision making. So that means, as I told you, once they are stuck on the dead end, they are hard to escape from such a local minimum. That's why 0% bot noise, 0% bot noise or the perfect bot cannot improve the coordination issue. But at the same time, with bot noise is 30%, the bot destabilizes the entire social networks that are hard to settle down in the optimal state. So the bot with 10% behavioral randomness create the ideal landscape of noisiness for the entire network to solve conflict. The bot increase the randomness of central player here, who are often stuck in the local minimum. At the same time, that the bot reduce that of the peripheral players who never encounters a reasonable conflict. So through the influence of the behavioral randomness, the 10% noise bot reduced unsolvable conflict, not only of themselves, but also the entire network, including the links between humans and connected to the bot. This is how the bot with small noise at central location improve group coordination. Okay. So let me return to the original research question. How can individual bot facilitate collective action to solve the coordination problem? The answer is that some random behavior at central network location help social coordination. The experiment suggests we may need central person or bot who sometimes make an error. Even though they look irrational and often annoying to us, we need it to facilitate social coordination. This research also shows the methodological benefit of the use of bot in social experiments. We can use a bot not only as a practical means, but also as a heuristic research tool to study the social dynamics of humans, other animals, even machines. We need to deal with the interaction between micro and macro structure. And in many social experiments, we often analyze the linkage from macro structure, for example, how network structure exists, then to influence individual behavior, that means the micro individual behavior. But using the bot into social experiment, we can also study other side. So that is how individuals affect macro level social phenomena, like this study. All right, so I would like to take a question at end of the talk. So please hold your question if you something have in my first talk. All right, so my lab applied this approach to other collective action challenges, such as cooperation and resource sharing. So if you carefully read my sentences here, it's somehow awkward sentences. For example, cooperation with defriending bot. Why? It's possible. But I would like to go to the next idea of this human-AI hybrid. So this system is social level integration between human and AI agent, and it has become popular, especially in online spaces around 2020. Since then, with further advancement, AI technology is now becoming more of a commodity. Like ChatGPT, each individual uses AI tool while making their decision. In other words, machine intelligence is becoming integrated into human intelligence at the individual level, like many of you studying in terms of human augmentation. So recently, my lab has been expanding this research theme with Shunichi to include hybrid actors of human and machines as another form of human-AI hybrid. As we examine the social dynamics of individual level, human-AI hybrid, and what's going on, social level, based on this hybrid actor, human-AI intelligence. I know it's kind of a little bit scientific fiction, but let me show the actual example, what we already have, this type of like integration. So let me explain about as a second study, I will introduce our first investigation from this view using a real-life driving coordination. This paper was published by PNAS last year, that's 2023. Let me explain this study's context. When you drive along a country road, for example, Yamba, you might experience this type of the things. One lane, two cars. You have two choices, go straight or swap. Of course, you just want to go straight to reach a destination, for example, to join a wonderful conferences at OIST. However, the ongoing vehicle prevented you from doing so. So then the counterpart drivers also have an issue. That is you. So to avoid the collision, either you or your counterpart must give way and let the other go straight. This anti-coordination situation has been studied very classically, especially in game theory and political science too, which is called chicken game. The right table models the interaction structure. B, here is the benefit, the represented benefit you can earn by reaching your destination straightforwardly. For example, joining the Shun's workshop on the time. Okay? C represents the cost you will pay by swarming off-road and losing time and rate for the conferences. Then you might be miss the very important talk by Pedro. Okay, that is cost, huge cost to you. So what's interesting here is strategic interdependence. Your best choice depends on your partner's choice. So when your partner goes straight, you should swap, of course. But when your partner swap, you should go straight. This is also true with your partner. So people often wait for their partner to make a decision when you face this type of the situation. But when both parties delay their decision while driving, they eventually come to a collision, which is the worst outcome. So there is no optimal solution in one-shot interaction here. Yeah. So either party, or maybe both, have to pay the cost to this situation. But if the interaction is repeated, there is a socially optimal solution that is alternating reciprocity. When the two parties take turns giving way, they can equally benefit from this anti-coordination situation. Mathematically speaking, the two-round benefit, for example, of alternating reciprocity. So that means that if you swap goes, then other counterpart goes right, then next turn you go straight while your counterpart swap. That is alternating reciprocity. Then you can see that average benefit of this alternating reciprocity is B minus C by 2. But if you swap every time, your benefit, of course, B minus C on average. So that means that this alternating benefit, reciprocity give better benefit to you. When see real world interaction while driving, actually we can see many reciprocal actions, such as taking turns, giving way. So the good news is that humans are intelligent enough to develop reciprocity to address this kind of the joint problem. But now machine intelligence is present in our interaction, such as driving assistant for safety. I took this picture from the Nissan website, which explained how their autonomous assistant works. Actually, this system is not a hypothetical one. It has already been installed in many Nissan cars and other cars by other companies and driving on the real road. So how does this kind of AI assistant affect our norm of reciprocity? That is my research question of this PNS paper. So in theory, safety assistant actually transforms the interaction structure. That, I think, is an interesting way in theoretical perspective. People won't crash, even when both go straight from subjective perspective. So objectively, of course, if two cars go straight, then go to crash. But with assistant from individual perspective, if people believe the technology, okay, they never crash, even both parties go straight, because this driving assistant automatically swarm. Okay? Then here is B minus C asterisk. It changed from 0. Then if C asterisk lower than C, so that means the cost of automatic steering is less than the cost of manual swerving. Now it's B minus C asterisk larger than B minus C, right? Very simple math. But the point is that now is the arrow is not like this. So it's not like this. The previously the arrow is like this and this. That indicated theoretical interdependence. Then now the arrows both go up. That means that regardless of your counterpart choice, your best choice is now is go straight. So now is the theoretical interdependence gone. Then the question is how alternating reciprocity exists with this driving assistant. Okay? Does it make sense? All right, so to examine, we have tested the theoretical prediction by operationalizing the theoretical concept of the chicken game in the real world. This experiment involved a palm-sized robot remotely controlled by online participants that you cannot see in this picture. So this boy is not a participant. He's just watching how grown-ups are struggling to be nice with each other. So it's a good, good educational material for kids too. This slide shows the overview of the cyber-physical experiment system. I don't go into the technical details today, but I can say a lot of cutting-edge technology works together to address many technical difficulties in this remote control operation, thanks to Shunichi and Kai Shimiz, maybe around here. We actually perform experiment very smoothly without making participants realize this technical complexity. So this slide shows the interaction environment and the user interface. So each user controls their physical car remotely by very simple view. So two players interact with the first-person view from the onboard camera over 10 rounds. So repeated interaction. And each player earned more money per round when they reach the pink taped goals earlier. So like the card coordination game, the participant economically incentivized. But here it's just simply to reach the goal quickly. That's it. But they also know like, oh, the other person also going to this way. And the other also have the incentive to reach the goal as soon as possible. When they driving off, and when they drive off the road, their driving speed decreased by 75%. So resulting a loss of time and monetary bonus. This situation is exactly the iterated chicken game. So within this basic setup, we manipulated two factors, active safety assistant and messaging capability. So we controlled active safety assistant in 4 ways. So in the manual condition, when people drive, then the car detects some obstacle on the head. For example, here is a distance D1. Even in the manual driving, they got some warning. It's almost crashing, but that's it. So that means that they needed to control their car to avoid a crash on their own. The auto braking condition is that with warning, the car automatically stops at a distance D1. But still, they needed to avoid the obstacle on their own. Okay? The auto steering here is after warning, even after warning, the car more approaching the obstacle here, like a D2, the car automatically swerves to avoid the collision. So in contrast of the other condition, in the auto steering condition, people doesn't need it to control the car to avoid the collision. Okay, but this is the automatic part is only the emergency case. So that means that human participant can do the same behavior as manual driving auto braking as they like. Okay? Then the last fourth condition is combined of auto steering and auto steering. And I'll explain why this combined condition is interesting in this experiment later. The other treatment is messaging capability. So independently of safety assistant, we also manipulated whether driver could communicate with each other. So in half of the session, participants have this additional button. It's saying go ahead and thank you. Then when they click this button, the message pop up in the view of the counterpart camera view. Show up like, hey, this person to go ahead, and then you can also say like a thank you or something like that. So in contrast of like a negotiation, human participant cannot negotiate in advance of the coordination. But with this button, they can show the intention of the behavior to other participants. Okay. So for example, if you click a go ahead, what does it mean is that not only I just swerve to avoid a collision, no, I actually swerve to you to give away, to go ahead. Okay, so that means with this go ahead button, even with the same behavior, the counterpart understands the intention of the behavior of that. Then we studied about how this communication improve or suppress the people's coordination situation. All right, so in sum, we evaluated 8 treatment combinations. Here is 4 by 2 in the experiment. And both parties were assigned to the same condition. Here is a pair study, so that 2 participants assigned the same condition, and they were informed their counterpart also had the same feature as they did. We also had 2 supplemental conditions, which I will explain later. So we conducted 15 sessions for each treatment combination for a total of 150 groups with 300 participants overall. Because we used the online participant for this study, even with the physical coordination, we can have this level of the group size for this study. All right, let me show the actual session like color coordination game is appeared. Here you go. So you can see some noise from here. So top view is actual view. I recorded. Then last view is like a recreating the trajectory and also the action from the recorded video. So you can see it's very like a consistency of this actual view and the recorded trajectory and the view. Here is the round 2. For example, yellow car said, go ahead, but do nothing. The blue car couldn't understand what it means. Then, okay, maybe I should swerve, but yellow car too quick, then crash. Then goat hand comes in, then separate them to them. So yeah, then I can show you a little bit, wait a little bit. Yeah, here's round 3. Again, the yellow car is doubtful go-ahead messages. Then blue car could not understand. But show again, then yellow car do it again. Then this is round 4. That is round 4. Yeah, then yellow car do it. Same things again. The blue car really got angry. Then like this. Okay, so actually this is one of the worst coordination in my observation. So let me show like a coordinated one. So this is another session again. 2 persons control this car from thousands of miles away. Okay, this is another session, the other people. Then here is again like blue car swap and the yellow car is going straight. So that's good, the same as last video. But here, yeah, I'll speed up 8 times. And you can see yellow cars swap, then blue cars swap. Again, like they are stranger, but beautiful, peaceful coordination. This is alternating reciprocity. Then let me show the other type of the sessions, interaction. Again, like here is another session with different people. Then here is that they swap, they delay the swapping. That's why they cannot like coordinate well to one person goes right. Then both cars swap and reach, then 8 times swap. Same things go over and over again. Somehow beautiful, isn't it? Right? But this is both chicken. So both sessions exactly same except for the driving assistant. The first session comes from manual driving condition. The last one coming from auto steering assistant condition. So let me show the aggregated result right here. So it's a bit complicated. So let me explain one by one, like previous color coordination experiment settings. The color here is x-axis and down. So I told you here 10 rounds for each pair. And this bar indicated each pair. So this is actually raw data, not aggregate, not average or something like that. So aggregate here is 1 pair, 2 pairs, 3 pairs, 4 pairs, and the 15 pairs for each serial. And the color indicated what they behave each round. For example, yellow means a unilateral turn by yellow car means the yellow car goes swap and blue car goes right. Blue means the blue car goes swap and the yellow car goes right. Gray means the both cars swap, like you show, like both chicken, and red means the crash. So in the manual condition, some of them had reciprocal turns. Reciprocity showed up more often when they had a message function. So reciprocity means that yellow and blue cars take turns. Right? That's why taking turns, giving way. So here is indicated the bold line. That means the reciprocity. Then auto braking. It's also great. In the auto braking condition, several pairs have such a reciprocal session, especially with messaging function, the auto system significantly increase the occurrence of reciprocal action. Then interesting things happen with auto steering session. They clearly differ from other conditions. Most interaction result in the bilateral turn, that is both chicken. While people had almost no crash, they also had no reciprocal turns at all with safety assistant. As I noted before, they could exhibit same behavior as a manual and operating condition, but they changed their coordination mode drastically with the presence of auto steering assistants. I'm discussing the last combined condition of auto braking and auto steering. You can see a little bit different from auto steering, but still very low frequency of reciprocal action with this combined condition. That's interesting because with this combined condition, auto braking, auto steering, because they have auto steering, sorry, here is no crashing, but both auto braking and auto steering, they did not crash. So that means that this is not zero, right? Because they are swapping. But at the same time, because they also auto braking. So that means that using auto steering system, they take more time to do that. So mathematically speaking, if they take turns giving way so that they display action, they actually earn more than this both chicken condition. But still, they did not have reciprocal action. So that means here the C asterisk is actually larger than C. I intentionally designed this condition, but still they do not have reciprocal action. So that means simply in the presence of auto-steering assistant, people actually collapse reciprocity and cannot recover it. Even the economically does not make sense. All right, in contrast of typical behavior experiment like my color coordination stuff, this experiment allowed us to examine the trajectory and temporal speed of each player's driving, like this. So using these trajectory data, we evaluated their social value orientation in an X-Y coordination of reward to self and reward to others. So in contrast of traditional economic theory, like a rational theory, we humans show the various altruism in the world. So that means that we are happy not only rewarding to self, but also rewarding to others. Okay? That is the current understanding of human behavior. So that is called social orientation, social value orientation. Now here is I show indicated dot is each individual driving trajectory, x-axis reward to self, and y-axis reward to others. So that means if you drive to a main road, even the counterpart going straight, that means that you earn to yourself, right? Because you can reach the goal as soon as possible. So that means if you drive the main road, even your counterpart going straight, that means your behavior is more reward to self. But if you swap quickly to spatial road, the other protein going road, so that means that you give the reward to others. So then I calculated each dot like this, x-axis reward to self and reward to others. Then you can see the huge variation of the driving trajectory. Some people behave more altruistic, giving reward to others. Some people more reward to self. Yeah, this is typical, not only my experiment. Many other experiments and empirical studies show this variation of human behavior. That's good. With auto-steering assistant, about 90% of the time, people behave selfishly without giving reward to others in our experiment. But in the presence of auto-steering assistant, this social variation converge into this line, almost behavior on this Y. So I used randomized control procedure in this experiment. Does that mean that these differences does not come from human personality? This difference comes from actually integrated machine intelligence. All right, so finally, we studied how AI assistant can change their social coordination mode by not only changing the economical environment, but also intruding on the normative dimension. So in the supplemental experiment, we change auto-steering assistant activation, deactivation in the middle of the session. So here is first 5 rounds, people drive manually. Then in the middle of the session, we say like, hey, lucky to you, you have now auto-steering assistant. They change drastically with the introduction. So again, like they starting like this driving just after 5 rounds. Then what's happened? The opposite. So that means when people drive auto-steering assistant, then they remove, like Pedro's experiment. This here is not good means like a Pedro study. They're consistent after removing the assistant. So that they never recover reciprocal actions after auto-steering. So once they introduce auto-steering assistant and they drive selfishly, they cannot trust the counterpart anymore, right? Why you can believe once you swap, they can give me the load next round. It's hard to believe. So this indicated that not only this behavior changes due to the economical adjustment, but also the corruption of the social norm. So here is the summary. We use a novel cyber physical experiment to examine change in social dynamics that can occur in hybrid actors of human and machine engaged in the collective action. Our focus was on the social impact of basic AI assistant in 2 forms, auto-braking assistant and auto-steering assistant. So although the differences between the 2 systems may seem very minor, so one is control the speed, the auto-braking, one just control the direction, right? But from a social recapitulation perspective, the effect vary significantly. So auto-braking assistant actually support human agency, human decision that facilitate communication and reciprocity and maintain diverse social preferences. On the other hand, auto-steering assistant actually replace human decision. That actually suppress the communication and the reciprocity and convert social preference to self-interest thinking. So the last experiment, the combined conditions show like the auto-steering effect is actually dominant over the auto-braking assistant. So that means that once we introduce auto-steering assistant, we have this type of effect, suppression of communication and reciprocity and focusing of people to self-seeking behavior. So many of you actually working on the human augmentation. Please be careful. Maybe your system might focus your participant user to more self-interest seeking. Finally, I would like to show this video again because I really love this one, the chicken game with auto-steering assistant. And you can see this beautiful coordination. Yep, but actually, we know this is not the result of human coordination. People have no willingness to coordinate because people just leave their decision to machine. That's why this is the result. But when I show this video to animal behavior people, okay, they say like, wow, wonderful coordination. This is like fish schooling. Okay, so that means that if we see this is hybrid actors, not human, hybrid actors, they are actually succeeded in the coordination well. Do you understand? So that if we see humans from this coordination, humans have no willingness, this is the failure of coordination. But if we see a little bit step back to see this actor is one, not human, human and machine hybrid, this coordination is perfect. Then now as machine intelligence become more popular, I expected this type of not driving coordination, many other dimensions. Apparent social coordination could be improved, but we are not sure that comes from human intention. So that means that new research question may arise is that where are the boundary of you? So AI assistant can be a part of you, even if you deny, I am different from this AI assistant like ChatGPT. But at least in other eyes of others, your behavior outcome actually is combined of you. So that means that my question is that where are the boundary of you? So this is a perfect topic for this workshop. That's all for me. Thank you.